Hi, I'm Mr. Franklin. In this video, I'm going to go over page 8 and 9. There are some very specific words we're looking for some of this, so please pay attention to these and correct your worksheet. So number 1, the fundamental property causing the force between protons and electrons is charge. The charge of an object is what's driving all of the stuff we're talking about in this unit, because once we have a force, then we can have all kinds of other things happening, like voltage and current and all kinds of stuff. But it all starts with charge. Rubbing certain materials together can create static electricity. So this is you rubbing your shoes against the carpet and then shocking somebody. Static electricity. Draw a sample atom and show the 3 types of particles, their locations, and their charges. Okay, I've shown you this before. I do this a little bit differently. This drawing is acceptable, very acceptable. Protons are positive and they're in the nucleus. Neutrons have no charge and they're in the nucleus. And electrons go around the outside, and they're negative. So one of the ways I do this a little differently, and it's just because I've drawn a million of these, I will just go ahead and do P positive, and then N0, and then N0, and that goes in the nucleus, and then I'll draw my circle, and then I'll put my electron, E negative, and I'll put my E negative. Now notice the electrons are on opposite sides of the atom. We're not going to be grading you too tough on that, but technically that's actually what happens. Why? Because what does a negative charge and a negative charge do? Negative charge and a negative charge repel. So they're on opposite sides of the atom, but they are held into the atom. Okay? Because opposite charges attract. And there's some other stuff going on as well that we may or may not get into. Show the formula for Coulomb's law. Force equals K times Q1 times Q2 divided by R squared. Keep in mind that Q1, it's Q. The 1 is a subscript. It's just an identifier. It's the first charge. Q2 is the second charge. Those aren't actually numbers that go in the equation, but the 2 is the second charge. So just keep that in mind. I think most of you figured that out by now, but just from reading stuff, some of you have not. And it's confusing because down here we have an R squared, so this 2 is meaning we're going to square that distance. One of the things that normally we would point out in class is, what does this equation look a lot like? It looks like the gravity force. F equals G m1 m2 over R squared. Mathematically, they work very similarly in process and how you do the numbers, but this force, answering number 5, relative to the gravity force, the electric force is much larger, impossibly larger. These are connected. This similarity is what has led scientists to pursue ideas like string theory and trying to find the theory of everything. It's really important that you notice when scientists observe something that's different but yet very similar, we start looking for, well, how is this connected? And so that's one of the quests of science. This connection has not been made. This is one of the open areas of physics that scientists are trying to figure out. How can we connect this? I've mentioned before in passing that there are 4 forces of nature. We have really only studied 2. We've talked about a third one, but we've talked about the electric force, this one. We've talked about the gravitational force. There's the weak nuclear force. There's the strong nuclear force. But basically, modern physics has taken these 3 forces and shown mathematically they're actually different aspects of the same force. They are connected, and it is quite a bit complicated to explain, but those have been connected. Gravity still has not been connected with these other 3, and that's one of the areas where modern physics is trying to delve into and figure out. Number 6, if you hold 2 electrons, if you could do that and then let them go, what would happen? 2 electrons are 2 negatives, so a negative and a negative repel. If you had 2 charged objects, what would happen to the force between them if the charge on both doubled? So look here, F equals K, Q1, Q2. If you double the charge of the first one, double the charge on the second one, You got 2 times 2, which equals 4, so the force would increase by 4 times. Number 8, if you had 2 charged objects, what would happen to the force between them if the distance between the objects doubled? So if you take them farther apart, we are dividing, so the distance is dividing, so the force is going to get smaller because this is going to get bigger, but it's also squared. So if the distance doubled, we have, so 2 squared equals 4, but because they're going farther apart, the distance doubles. They're farther apart, this is getting bigger, then the force has to get smaller by 1/4. Bottom line is if these are the 2 charged objects, if I double the distance, the force is going to get smaller. If I halve the distance, the force is going to get bigger. So if I double the distance, 2 squared, the force is going to get smaller by 1/4. So we square how much the change is, and then it's on the bottom of a fraction. Here, though, we're going to halve the distance. What's a half squared? A half squared is 1/4. But if we put that on the bottom of a fraction, what's 1 divided by 1/4? 1 divided by 1/4, that's like dividing by a fraction. How do you divide by fractions? You multiply it times the reciprocal. So 1 times, what's the reciprocal of 1/4? That's 4/1, which is equal to 4. So the force is going to increase by 4. 4 times bigger, the distance gets smaller. 4 times bigger, the distance gets bigger. It's 4 times smaller, the force. 4 times bigger, 4 times smaller. If I change it by a third, 3 squared, which is 9. So if it tripled the distance, then it would get smaller by 1/9. If I cut the distance by a third, then it would get bigger by 9 times. So that's as deep as we're going to go into this. Be sure that if you run into a problem with this, that you ask me questions. Okay? Number 9. What is the law of charge? Opposites attract and likes repel. Like charges, negative and negative, repel. Positive and positive, repel. Positive and negative attract because they're opposite. What is current? Current is the flow of charge. And the equation for current is I equals Q divided by T. It's almost a trick question because only physicists use this equation for current. Okay? Charge is coulombs per second. That's supposed to be an S. Coulombs per second. But that's also known as the amp, okay, the ampere. A coulomb, 1 coulomb, is comprised of a mind-boggling, inconceivable amount of charge. 1 coulomb has basically the equivalent of all the sand and all the beaches of the world amount of charge, okay? Mind-boggling amount of charge in 1 coulomb. Current flows easily through a conductor. An insulator is a material that keeps current flowing. So insulators we also use for heat. So styrofoam cup holds in heat, but it would also not conduct electricity. So if it's a conductor of heat, generally, there's exceptions, generally it's a conductor of electricity as well, and vice versa. If it's an insulator, it's generally a insulator for electricity as well as heat. But an insulator keeps things from flowing, a conductor allows it to pass through. A resistor is a material that allows some current to flow, but creates friction. It resists it, and the friction results in heat. An example of a good conductor is gold is a really, really good conductor, copper, silver, basically metals in general, and that's because of their structure determines their function. It has to do with d orbital electrons, which you'll learn about in chemistry, and metallic bonds. An example of a good insulator, plastics, rubber, styrofoam, and that also is because of their structure. It does not allow electrons to flow easily, but you can take a rubber balloon and rub it against your hair actually, and you can charge the balloon. Current is measured in amperes. It's named after a French gentleman who did a lot of work with current. We often shorten it to amp. That's 12 amps. That's 2 amps. Okay, but it's actually the ampere, but we'll shorten it to that. And the symbol is capital A. Current is how much charge goes by in a certain amount of time. That's a repeating of the equation, Q divided by T. Resistance is measured in ohms. The symbol is a horseshoe. It's the Greek letter omega, and it's this little horseshoe. Generally, when we're typing it in the computer, we'll type ohms unless we can enable the Greek text. Ohms is the resistance. If you look on your battery or your charger plug, you might see this symbol. If you do any kind of speaker work, like you're setting up a stereo system or working on a car, you might see this with some of the electronics because this is a rating for their resistance. A device that has resistance is called a resistor. Draw the circuit symbol for a resistor. It's a line with some squiggles. So in other words, the current is flowing. So we got the current is flowing, it's flowing, it's flowing. Oh, it's not so easy to flow. I got some resistance, but I can still move through, and now it's moving. So when we're talking electricity, a lot of times it's easy to think of it like water. It's not water, but it flows like water. Resistors control how the current flows and how it works in a circuit. One way voltage is created is by separating charges, like is done in a battery. When protons and electrons are separated, the separation is called a potential difference, similar to gravitational potential. If we raise an object off the ground, I take my bowling ball and I raise it up off the ground, and now I have my bowling ball above the ground. What happens as soon as I drop it? It goes to ground. So that's the same thing that happens with the battery. The battery separates the charges, and then you plug it in, put it in the device, and it allows basically the charge to drop to the ground. Those are actually electrical terms. It causes charge to flow. And if it's flowing, it's called current. So we use the letter I for current. A voltaic pile is just a battery. That's in the video notes. Define voltage in words. Voltage is the amount of work per charge. Voltage goes across a component in a circuit, and current goes through the component. So there's a word that got deleted, so make sure you insert current. Voltage goes across a component in a circuit, and current goes through the component. The voltage is like the potential energy. It's the separation here. Okay, so it's across the component, but once you have this voltage available, the current will actually go through the component. Draw the circuit symbol for a battery. So this is actually, the simple version is this. You have a long line and a short line. This is the positive end of the battery, and this is the negative end of the battery. Most of this is actually just a review of vocabulary and maybe going more in depth on what the vocabulary is. So that really is your most important thing to study. All right, that's all I've got. Thank you very much. Bye.